Hello everyone. So today we are going to do a multi-phase volume of fluid simulation. So in situations where you have to track the interface between two fluids, or you have a free surface flow, or where you want to capture the interface such to account for surface tension effects, then in those cases we have to track the interface in an accurate way. And in multi-phase simulations we have several methods for that, and one of them is the volume of fluid simulation. So in VOF method we essentially solve for the transport of a phase indicator function like the volume fraction along with the momentum. So that's basic thing with VOF simulations. In my case I have a container and I have two immiscible liquids inside. One is petrol and one is water, and I have a small bubble of the petrol inside the water region, and I am using the VOF method to track this bubble rising through the domain. Okay, and this is just a case I made to demonstrate how to set up a VOF simulation. And also the other thing which we will cover is we use a axisymmetric case for the simulation. So you can consider this domain to be a three-dimensional cylinder, and we are using axisymmetric case, so that's the section view of the domain. Okay, and we can use this axisymmetric assumption at situations when you have an axis of symmetry, and also you need to have a laminar flow case. So we can't use 2D or axisymmetric approximation with turbulent flow, since they are inherently three-dimensional. In our case we can use that. Okay, and these are the dimensions of the geometry. So let's see how to set up the simulation. So I have created a new simulation and named it bubble rising, and now we can create the geometry. Regarding the geometry, you have to consider two things. We are doing a 2D simulation, so we need to have the domain in the set plane, and also the axis of rotation for the axisymmetric simulation must be along the x-axis. So that's the two things that we have to consider. So I'm creating a sketch in the xy plane, and like I said, since I have the axis along x, I'm just reorienting it to view it properly. And this is significant when you define the gravity in the physics. You have to remember that to assign the value of g along the x-axis. Okay, create a rectangle and modify the nodes according to our dimensions. Okay, so we have the sketch. Create a small extrusion. Okay, so we can easily pick the surfaces for the boundaries. That's why we created it as 3D, and I think that's the easiest way. Okay, update and close, and this we can rename it as our domain and create a new geometry part. Okay, I have this geometry scene created. I'll just pull this into frame. Okay, and by default we have the entire surfaces as a single combined surface, but we need to have the set plane and axis face, so we can split them by split by batch operation. So this will be our axis face from which we will get the axis, and this is our set plane. Create, and the rest of the lateral faces will form the walls. Okay, So next we can do the badging operation prior to 2D meshing. So inside operations, mesh batch for 2D meshing, select, okay, and you have the indicator for successful badging. Okay, next we need to assign the parts to the regions so that we can do the meshing. Close, and you can find the same here. Okay, now create the mesh, 2D mesh. So I'm using a quadrilateral mesher. I need a uniform Cartesian kind of mesh for simplicity. So the thing is, we have to make sure there is enough resolution with the interface. So it's a thumb rule to use at least 20 cells within the bubble. So I'm just following the same, and I'm using a base size of 0.1 mm. And to get a uniform mesh, I reference all the other dimensions to be 100% as the base size, and also I use a specified growth rate which is negligible. Okay, now create the mesh. Okay, so the meshing is done. Create a mesh scene. Yeah, so that's our mesh. Okay, and the next we need to set up the physics. So select models. We are not doing two-dimensional, but we are doing axisymmetric case, implicit unsteady, multiphase material, volume of fluid simulation, laminar, also enable gravity. Okay, yeah. Now we can define the different phases and materials. So inside multiphase, go to phases and new. So the primary phase or the continuous phase is water. Select the models, liquid and constant density. Close. You can specify the material properties here. By default it will be water for liquid. Then you can change the density if you want. I'm using 1000. Dynamic viscosity 0.89. Okay, then you need the second phase. So phases, new, rename it as petrol. Select models, liquid, constant density, close, and modify the properties from water to petrol. So I have a density which is equal to 700 and a dynamic viscosity which is 5e to the power minus 4 Pascal seconds. Okay, next we need to create a phase interaction. We define the phases, we need to define how they interact. So new, water, petrol, phase interaction, and it's basically surface tension that governs the interface. We can select the models and you can find surface tension force. Okay, and inside surface tension force you can specify the value of surface tension, and I'm using 0.03. Okay, and inside VOF node you can find the interface tracking scheme which is used. So that is HRIC, I'm using it, high resolution interface capturing. And inside reference values you can specify the gravity. So say right now it's in the y-axis, you have to change that to x-axis, 0.0 and minus 9.81 along the x. Okay, and the important step in physics setting is to specify the initial condition or the initial distribution of the fluids. So we have to do that here. And I have multiple regions of, for that I'm using a field function. So new scalar user defined field initial distribution. Okay, and we can change it into what? Modify the definition. So I have already created this field function expression. So this is a conditional statement, so I can explain. So the first statement says that if the x coordinate is less than 0.014, which is 14 mm, and the second statement which says that x minus 4 mm whole square plus y square plus z square greater than or equal to radius square. So that's the spherical region, okay, equation of sphere, and the greater than or equal to means outside. Okay, so if these two statements are true, so the question mark means they check if it's true, and if it's true the value will be 1. Okay, so we intend to use it as volume fraction definition for water. So that means if these two statements are true, then that region will have volume fraction of water as 1, and the colon indicates else, and all those regions which doesn't satisfy this criteria get the volume fraction value of water as 0. Okay, so that's how the statement works, and you can make similar expressions to define different regions. Okay, so I have used that, and you can specify it here. And in the volume fraction definition method you have composite n minus 1. I'm using it, and it works basically like if you have n elements, you specify the volume fraction for n minus 1, and the nth term, nth volume fraction will be computed by the program. So in our case we have 2 elements, petrol and water, so we define only for water. Okay, and if we had 3, we would have defined for 2. Yes, so for water, instead of constant, use field function and select the field function that we just created. Okay, now coming to the boundary conditions. So by default the axis is considered as a wall. We have to change that, and since we enable the axisymmetric case, we should be able to find this axis type boundary. Okay, yeah, if it's in the 2D case then you can't see the axis, so make sure it's in the axisymmetric case. Okay, then inside the walls you can perhaps change the contact angle if you are interested in wettability, but for me in this simulation I don't want to consider any of it. So by default the contact angle will be 90 degrees. Okay, then you can set the mass momentum source terms for each phase as if required. I'm not using them. Then coming to the solvers, you have to specify the time step of simulation. So I'm going to use a 0.5 milliseconds as my time step size. So we have to monitor the CFL number and then decide on these things. So we will also use multi-stepping. So the thing with multi-stepping is that you can get a sharper interface by involving inner iterations to the solution of volume fraction transport, and you can reduce this diffusion. Okay, so for that you have to change it from single step to implicit multi-step. For our case it's safe to do so, because since the only time scale involved is the motion of the bubble and not any dynamics in the flow field, we can use it safely and get convergence without any issues. But if you have a very dynamic flow field and then you have conflicting time scales, then the flow will change very rapidly. That can have in that short time duration the interface can change a lot. Okay, and when you have such dynamic conditions, then it will be tricky to get a converged solution with multi-stepping. So in my case, it's okay. I can get better solution by enabling multi-stepping. Okay, so I have enabled that, and my inner iterations for implicit solver will be used as the same step count. Now inside stopping criteria, I'm using 20 inner iterations, and you can also modify them by monitoring the convergence. Okay, I'm using just 2 seconds, maximum steps 2000. And next is to set up some post-processing reports and scenes. So for reports, I have 2 things to do. I'm monitoring mass conservation error for each phase. So ideally, during the solution, the value of this error should be close to 0. Okay, so that's one way of tracking how good the setup is. And also you can, by monitoring the variation, you can also see how the convergence. And also one for petrol, you have to specify the phase here. Okay, and you can create, monitor and plot multiple plots. Yeah, okay, so we can close them for the time being and create new scenes. I need to monitor the volume fraction of petrol, so this can be volume fraction petrol. Okay, and you select the function. Okay, and you can orient. Yeah, for better visualization, we can actually transform this view to include the symmetry at the other half. So for that, we need to create a small transform inside here, inside tool transform, create a graphic symmetry transform. And for axisymmetric case, we need to specify 0, 1, 0, 0 as the coefficients of the plane, symmetry plane definition. Okay, and do that, and then you can find inside scenes scalar, or if you can go to the properties, then you can find transform, select this. Okay, then you should see the entire view. Okay, maybe you can hide the outline. Yeah, and also modify the basic stuff. Yes, and if you want to create animations in future, then you might have to capture the scenes. So I'm doing that. You give the trigger as time step, so it will save after time steps. Then enable save to file, then you specify the directory that you want to save it to. Okay, I have created 2 folders. Yes, open. Then you need to have a scene for velocity, so copy paste this and modify. So this can be velocity. Modify the function, need velocity magnitude, and I'm keeping this as 0.8 as the maximum value. Okay, and what else? Yeah, perhaps you can add a scene to monitor the CFL value also. Yeah, I'm not defining anything else but the function. Yeah, okay. So we have the scenes, maybe rename this. Okay, so we have everything. Yeah, and one more thing which can be useful if you run for a long time, that's to do auto saving. So you can enable auto save, and you can here modify update iteration. Instead of iteration, use time step, and I'm giving 100 time steps. Okay, so it will auto save after every 100 time steps. Yes, so that's pretty much it. Now if you go to the volume fraction scene, and if we initialize, then we should be able to see the initial distribution of petrol, and this looks fine. Okay, so I think we are good to go. So let's run the simulation and see if it's diverging or not. Okay, so the residuals are going down, that's fine. So I'm not bothered about the convergence, right? But it's not diverging, so that's good. So let's wait and see how the bubble moves and how does the interface change over time. Okay, also one more thing, maybe you can see the CFL number here now. So that's below 1 and going into 0.78. So that's okay. So we can close this tab, and so that's good. We can wait for the results. Okay, so the simulation ran for a number of iterations, and let's check the results. So first of all, the volume fraction scene. Using the scenes, I have created an animation, so let's check it out. So I used a Python script to stitch the images into a video, and this is the output. Maybe I can increase the speed. So you can observe this phenomena called coalescence cascade, where you have bigger bubbles or bigger droplets transforming into smaller and smaller in a kind of a repeated cycle. So the petrol bubble actually coalesced with the petrol region, and then as a result of that coalescence motion, the surface tension actually propelled a smaller water droplet into the petrol region. Okay, so until this formation of the droplet, everything was quite fast. Then it started to be very slow in response, like the newly formed bubble is moving very slowly, and also it's kind of oscillating. Okay, we can always calculate this terminal velocity based on the net forces acting on the bubble, so or the droplet. So in our case, we have this buoyancy force, and also the drag force and the weight. Okay, these are the primary forces. So based on that, we can calculate the terminal velocity. So if we calculate the terminal velocity, so that would be like this. You basically write the equation of motion, and then you find the velocity from that. And if you plug in the values of water and petrol for a particular radius of the bubble, so in our case, we can actually measure the diameter of the bubble by just using the scale, and it's like 0.5 mm diameter. So I have used that value in the calculation here. Okay, and then you found the terminal velocities around 0.082 meter per second. Okay, so I checked the velocity plot during this time, and the value is around, the max value is around 0.082. Okay, so I have clipped the maximum, but as you can see in the condo, there isn't too much above 0.082. It's only less than or 0.082. It won't be accurate, and clearly it's not moving at this speed, so there is something more which is in the play. So let's see a zoomed in version of what's happening after this primary bubble formation. Yeah, so this is after 1 seconds of physical time. Then you can see the smaller droplet, which is actually kind of oscillating, and also you can see a small film of petrol sticking to it. That's why it has a yellow shade, 0.5 volume fraction, which means there is a mixture of it. Okay, and also it's kind of like oscillating and moving down slowly. So you have this some additional physics which is causing a more resistance to the return of this droplet. Okay, with smaller bubbles it can have very low terminal velocity, so it kind of feels like it's suspending in the region, but it's actually falling down in a very small pace. Okay, so I ran the simulation till 2 seconds, and it's actually moving like this far. And if you measure the distance which is left to be covered, it's almost 5 mm. So in a matter of a second or two, it will again merge with the water region. Okay, and after that maybe you can see a even smaller droplet. Okay, so that's the way this coalescence cascade work. Okay, so we can check the other results. So this is the residuals plot, and it's low after sufficient amount of time. Then you can monitor this mass conservation error plot, and as you can see, after 0.2 seconds the error is very small, which is like almost converged situation. Okay, so and I ran the simulation beyond that very far, just to see if the droplet again will it merge in meantime with the water region. Okay, but against my expectation it didn't happen. So I did some more analysis on the forces that can be responsible for that, and so these are the three things which can additionally cause some effects on it. So like I said, there is this small thin film of petrol water mixture on the outer of the droplet, and thus can have some effective density and viscosity. Okay, so if that value is somewhere similar to the petrol, then it's kind of floats in the petrol region. Okay, so that can be one reason why it's showing a slow return. And the other thing is the Marangoni effect, which you can find in a wine glass if you observe it. So there is the surface tension gradient. So due to this variation in composition of this mixture, this petrol water mixture on the interface, and this can cause waves on the surface also. Okay, or asymmetrical surface tension force, which kind of create a kind of an oscillating interface thing. Okay, and we could also see that in the scene as well. And finally you have this, yeah, like I said, the surface deformations which we observed in the animation. Okay, so maybe I can play it again. So if you can observe here, the shape of the droplet is kind of kind of unstable and oscillating. So that can be a consequence of this film which is surrounded by the droplet, and the composition difference and the surface tension effects on it. Okay, so even though it has to it will eventually coalesce since the motion is really slow. Okay, so that was something interesting to observe. I found it very cool to try out this simulation, and perhaps you can also try it out. Okay, so that's it. Thanks for watching.